Video, we'll talk a little bit about the Heaviside function and its use in differential equations. So the Heaviside function is a really valuable discontinuous function, and it is sometimes referred to as a step function or a switching function that goes from 0 to 1 at some time t equals a. So it's defined as follows. The symbol that we use, and there are various notations for this, but for some reason we've clung to the notation calling this function u subscript a of t. And the a, as we'll see in a second, specifies the time at which the signal goes from 0 to 1. So the function, or the signal, produces a 0 for all times less than the specified or desired time that it turns on, and then at time a, the signal becomes a 1. Okay, that's a very simple function, yet it's a very powerful one. So, for example, u sub 3 of t is a Heaviside that goes to 1 at time 3, and here's what it looks like. So, up until time 3, the signal is 0 all the way across, no blips, burps, or anything like that. And at time 3, there's a discontinuity. So the signal goes from 0 to a 1. But the way we have this defined is that at time A, or at time 3 in this case, the signal is at an output value of 1. So can't be both values, of course. It can't both be 0 and 1. So at time 3, the signal becomes 1. And so we get this open dot indicating that at time 3, we should be looking at the signal of 1. Okay, so what are the uses for this? Well, it can turn signals on or off. So in electronics, we'll see in just a moment it can do that. So in some cases, this can be a power source that gets turned on and off. This could be a component of the rate of change in a differential equation that gets turned on or off. And we can also switch pieces of a function on or off, or both at some given times. That's something we'll investigate a little bit later, not so much in this video. Laplace transforms are a perfect way to use this function because one of the cool things is that even though this function is discontinuous, we actually never have to deal with the discontinuity. And so here's an example of a circuit. This is a basic RC circuit standing for there's a resistor and a capacitor in there, and this V sub C indicates that there's a charge across the capacitor, a voltage. A voltage is just a charge, and so we get current that flows, in this case, along this direction, but nothing is actually going to happen until the switch closes. So you can think about right now, this current state, the switch is in a 0 state, and when it connects and closes the circuit, that's in the 1 state. So here are the Laplace transforms we'll need. One is the Laplace of u sub a. Sometimes we'll just write u sub a, but the implication is that it's u sub a of t. And if you do the integral on this, and I'll just kind of do the quick outline of how this integral actually appears. This is, by definition, the integral from 0 to infinity of the Heaviside function u sub a of t times e to the negative st. And that's with respect to t. Now, u sub a, this might seem like a complicated integral, but here's how this really works. Up until time a, this integral is 0. Because if we integrate from 0 to a, we can break up this integral and basically integrate 0 times e to the negative st, because keep in mind that until time a, u sub a of t is valued at 0, plus the integral from a to infinity of 1 times e to the negative st dt. Now this integral, of course, is 0 because 0 times e to the negative st is 0, and there's no accumulation of area along that region, and so now we just need to integrate this. Well, e to the negative st, its integral is negative 1 over s e to the negative st, and this needs to be evaluated from t equals 0, to t equals infinity. And this is another reason the definition of Laplace transform is so powerful, because as long as I make the argument that s is greater than 0, then this becomes negative 1 over s times 0. But the second term is minus negative 1 over s e to the negative as, or negative s times a, because now I'm evaluating it not at 0, but at t equals a. And so this becomes a positive, and I get e to the, negative as over s, which is precisely this thing that we have here. Now here's another useful one. This will come a little bit later, and we'll actually have to use it to invert in our example. But what we can do is oftentimes what we want to do is let's suppose that I have some signal that looks like this. It starts at that vertical intercept, and I want it to deteriorate in this decay like this. But here's the thing. Let's suppose that I want this thing to be 0. So what I'm going to do is I am going to suppose that I don't want there to be any signal until this time here. And then at that time, I want the signal to turn on. Well, at that time, the value of this function actually starts at this blue dot, at this blue point, and decays from there. So this is a very valuable Laplace transform, because what I really want to happen is this function, I would like this point right here to actually be shifted so that the decay begins from that point onwards like this. And so in order to shift a function, we've got to recall some of our algebra. So if, for example, f of x, I'm thinking just back to algebraic skills, f of x equals x squared, then the function f of x minus 2, which means, f of x minus 2 means I plug in x minus 2 for x squared. And what I'll notice when I graph these functions is that if I graph f of x, then f of x looks like this. But if I graph f of x minus 2, which is this one here, then that's going to be the same function, except it's going to be shifted over to the right 2 units. Okay, so this makes sense that we would want a Laplace transform like this. I want this function to turn on at time a, but I want it to turn on a function that is shifted a units to the right. So for example, let's suppose that I want to take the Laplace transform of u sub 5 of t, and what I want is to have the function, let's say I want to deal with, in fact, let's say f of t is equal to t squared. So that means I'm going to shift t squared over 5 units to the right. So f of t minus 5 is equal to t minus 5 squared. So what I'm going to Laplace is the function t minus 5 quantity squared. And the right-hand side says, well, it's going to be e to the negative as. In my case, a is equal to 5, and multiplied by the Laplace of f of t. Okay, well, wait a minute. F of t minus 5 is t minus 5 squared, but f of t is t squared. So the Laplace of f of t, which is the unshifted version of that function, the unshifted version is just t squared, the shifted version is t minus 5 quantity squared. So this is the Laplace of t squared, and we know that that's going to be n factorial, which is 2 factorial over s to the 2 plus 1, or 2 over s cubed. And so that means that my result is going to be e to the negative 5s multiplied by 2 over s cubed. Okay, so that's how that works forward. Now we'll also need to use it backward in the next example. So let's move on to the next example. Solve dy dt equals 3y plus u sub 2 of t with the initial condition y of 0 equals 3. Well, first of all, what does this differential equation even do? Why would we introduce the Heaviside in there? Well, I'm going to go over to Desmos, graphing calculator. And what I'm going to do in here is I'm going to plot this function. But before I do that, I suppose we should define this, because dy dt is piecewise, and it's going to be split up into 2 components. Because the Heaviside is where the split will occur in this function, I'm going to look at this function for t less than 2 and for t greater than or equal to 2. But when t is less than 2, I know that u sub 2 of t is equal to 0. Therefore, dy dt will be 3y plus 0. When dy dt reaches 2, this guy becomes a 1, and so for all t greater than or equal to 2, I'll have 3y plus 1. So in other words, I will have an exponential function, and then I'll have an exponential function plus some stuff here. So I'm going to go over to Desmos, and the way I'm going to graph this is I have to use x, so I'll do x squared, not x squared, 3x, and I'm going to use the curly brace, and in this curly brace I'm going to say 0 less than or equal to x less than 2. Now, I don't really, or I could just say x is less than 2, but this function, usually we start at time 0, therefore looking at anything less than 0 does not make sense. And it's going to be valued at 3x plus 1 or x greater than or equal to 2. Simple as that. So what's going to happen is I'm going to have this rate of change function up until time 2, not including time 2. And you can see that it's undefined right there. And then the function 3x plus 1 when x reaches 2 and for all x beyond x equals 2. So that's what my differential equation is going to look like. It's a piecewise differential equation. Again, with using Laplace transforms, I never have to deal with this. So what would we expect this to do to y? Well, I would expect this to cause some aberration or some sudden change in y because suddenly the rate of change changes. And we will see that later on when we go to graph the solution. But again, the beauty is we'll never actually have to deal with this piecewise. All right, let's solve this. So the first thing I'm going to do is I'm going to Laplace both sides. And I know the Laplace transform of dy dt is s times the Laplace of y minus y of 0, which I know is equal to 3, which is equal to 3 times the Laplace of y plus the Laplace of u sub 2, which we know is plus e to the negative 2s over s. All right, so now I'm going to take my next step, isolate my Laplace of y's, s Laplace of y minus 3 Laplace of y, move that from this side over to this side, and move my constant over to the other side. So I have e to the negative 2s over s plus 3. And now I'm going to factor out a Laplace of y. So I get Laplace of y times s minus 3 equals e to the negative 2s over s plus 3. And now I'm going to divide both sides by s minus 3, and I get e to the negative 2s over s times s minus 3 plus 3 over s minus 3. Now before I go to invert, I already know that this will invert into 3e to the negative 2t because we know that the Laplace of e to the at is 1 over s minus a. 3e to the I messed this up totally, to the 3e to the 3t, because in this case, a is equal to positive 3. This, however, is a little bit more complicated because I don't have, if it were e to the negative 2s over s, I'd be in good shape, but it's e to the negative 2s over s times s minus 3. So what I'm going to do is I'm going to do a partial fraction decomposition here. And when I feed this to technology, I'm actually going to write this as e to the negative 2s times 1 over s times s minus 3. Because most technology will scoff at this and will not be able to actually incorporate that into the decomposition. So we're going to trick technology a little bit or exploit it, and we're going to enter this in. I'm going to go over to Wolfram Alpha. Let me see, I've got this open. I'm just going to type in partial fraction 1 divided by s times s minus 3. And lo and behold, I get an answer. It is 1/3 s minus 3, which is equal to e to the negative 2s times 1/3 times 1 over s minus 3. Factor out that 1/3 minus 1/3 times 1 over s. And I'm just going to move this over to the next page. So we have, and then plus, I can't forget this term here, plus 3 over s minus 3. I'm going to distribute this back in. Because now I can't inverse Laplace past this since it's a function of s, and the inverse Laplace operates on functions of s. So in my next slide, so here's what I have, and I can already invert. I'm going to call these 1, 2, and 3. And the reason I'm going to do this is because I know that when I invert both sides, excuse me, I don't need to write that there. I know the inverse of number 2. That's going to be minus 1/3 e to the negative 2s over s inverts back to u sub 2 of t. and 3 over s minus 3 inverts to 3e. The inverse of number 1 is going to be a little bit trickier, so I need to think about how I'm going to do that. Well, here is where we get to utilize the Laplace transform, the second one, which is this one here. And it may not seem entirely evident at first how we're going to use this, but what I'm going to do here, so that I don't forget and I don't have to deal with that 1/3, I'm going to put that 1/3 out front, because remember, I could pass constant factors in and out of integrals and derivatives, and that's all an inverse is really it's a derivative, if you think about it conceptually. So how is what I have here reminiscent of this Laplace transform and the inversion process? Well, what I have is I have e to the negative 2s times really what I can write as 1 over s minus 3. So what is this? What's required of me? What do I have to do at this point? Well, this says that if I want to invert something of the form e to the negative as times Laplace of f of t, I've got to identify what the f of t is whose Laplace transform would give me 1 over s minus 3. Well, I already know that. I know that f of t, the function whose Laplace transform produces 1 over s minus 3, is e to the 3t. In other words, the Laplace of e to the 3t is precisely 1 over s minus 3. All right, well, so now that I have that identified, in order to work my way to the right-hand side, in other words, in order to invert this, I need something of the form u sub a of t times f of t minus a. Well, this requires me to identify two things. One is f of t, which I already know, and the second component is a. Well, the a is exactly the exponent here, which is 2. So that means that I'm going to have something of the form u sub 2 of t times f of t minus 2. Well, I know that f of t is e to the 3t, so I can figure out what f of t minus 2 is. Well, f of t minus 2 is e to the 3t shifted over to the right 2 units. So this is going to be e to the 3 times t minus 2. And that's everything I need, because now I know that the inverse of this is going to be u sub 2 of t times my f of t minus 2, which is e to the 3 quantity t minus 2. And now I'm done. Now I know the inverse of 1, and so my final answer is going to be y equals 1/3 times u sub 2 of t times e to the 3 quantity t minus 2 minus 1/3 u sub 2 of t plus 3e to the 3t. That's my final answer right there. Okay, well, what do I do with this? Well, again, notice that we didn't ever have to deal with the discontinuity. But if I want to graph this, if I want to understand and visualize this function, I now have to break it up into pieces. So let's do that. So y is going to equal 2 different components. And what is my time break? My time break is at time 2, because that's the Heaviside I have in here. So for t less than 2, I've got to look at this. And then for t greater than or equal to 2, I've got to look at this. Well, what happens when t is less than 2? Well, when t is less than 2, u sub 2 of t is 0 here and here. Therefore, this whole term will be 0, because I'll have 1/3 times 0 times a function. And this will be 0 because negative 1/3 times 0 is 0. So all I will have for time less than 2 is 3e to the 3t. Now, when I reach time equals 2, the Heaviside function is valued at 1 here and here, and therefore I'll have 1/3 times 1 times e to the 3 times t minus 2. So that's going to be 1/3 e to the 3 times quantity t minus 2 minus 1/3. Well, this is valued at 1, therefore that term will just be minus 1/3. And the last term is still present. That's unaffected by the Heaviside function. There's not a Heaviside function component in that. And so now I have something that I can graph. So even here, we can see that at time 2, there's going to be something interesting that happens. We go from one function to another function. So let's go ahead and take a look at that. And we'll jump right over to Desmos once again. And let's do this. So we'll clear these out. And I know that the function is 3e to the 3x, or curly bracket, x less than 2. And I'm going to go 0 less than or equal to x less than 2 because I'm going to start at time 2. And I'm going to go to the next component, which is 3e to the 3x minus 1/3. Oh, wait, I'm going to put that term last. Jump back over here. So it's 1/3 e to the 3 times t minus 2. E to the 3 times t minus 2. Minus 1/3 plus, oops, I'm using t instead of x, plus 3e to the 3x. And I want to value that only for x greater than or equal to 2. Okay, so now I've got the both components graphed, so I'm going to have to zoom out a bit to see what's going on here. And I'm going to want to look at it for, let's see, I'm going to change my setting here. I'm going to go from maybe time -5 to maybe we'll say 6 on the x-axis. And let's want to change my y setting so I can actually see what's happening here at time 2. So I'm going to set this up maybe to 150, see if that helps. And nope, that doesn't help. That's not enough. So I'm going to have to go up a lot higher, maybe to, let's say, 500. And that's still not big enough. So let's go up to maybe 3,000. Will that be enough? That's enough. So if I follow this function, then I see that it's not altogether too interesting because not a ton changes. But if I zoom in at this point, you can really see that the function does break, and the function is fairly exponential. And then as I zoom out more and more, you can kind of see that the function goes from being a simple exponential to almost a very, very rapidly growing exponential after that point. So there's a break there, and that appears to be at around 1,210. So I'll just graph a line at y equals 1,210. So we can see more distinctly that this piece corresponds to this component here, and this piece corresponds to this component here. So I've been able to essentially effectively turn on another component of the rate of change function as we go back to a few slides previous, where we decided that this function would basically, the rate of change doesn't change by that much. It increases by a unit of whatever, 1 unit of y per unit of time, in addition to the 3y units of y per unit of time. And so we get this very interesting little break here. So this, as you can imagine, has really broad uses, but this just kind of demonstrates or kind of skims the surface of what we can do with it.